The standard model of particle physics is a collection of particles, interactions, and symmetries that, within the mathematical framework of quantum field theory, provide our best description of physical reality. The mission of the Center for Fundamental Physics at Northwestern University, the CFP for short, is to make highly precise measurements to test the standard model and unusually sensitive searches for new physics that is beyond the standard model. The students, postdocs, and professors of the CFP utilize novel quantum devices and methods, along with cutting-edge technologies to perform measurements that fit on tabletops without the need for large national or international facilities.
The electron's magnetic moment is the most precisely measured property of an elementary particle. We measure it using a single trapped particle that is cooled to its quantum ground state. This allows us to test the standard model's most precise predictions and set stringent limits on the new types of physics it might include.
We also trap a single positron from a radioactive source, so we can compare the electron to its antimatter counterpart. And this is to make the most precise test of the fundamental CPT symmetry that's within the standard model.
Quantum jump spectroscopy, quantum non-demolition detection, a dilution refrigerator, and a custom superconducting solenoid are crucial. Quantum limited detectors and special relativity are keys to a new generation of measurements.
Our ACME collaboration improved the sensitivity of electron-electric dipole moment measurements by a factor of 100. We're now looking for a further factor of 40. These are extremely sensitive searches for CP symmetry violation that are needed to explain a matter universe with essentially no antimatter, and to set stringent limits on physics that is not included in the standard model.
The electric dipole moment measures the roundness of the electron charge, which we detect using the exceedingly strong electric field within a thorium oxide molecule. 11 lasers, which are in drawers to save space, repair and detect the needed quantum states.
A new generation measurement uses an electrostatic lens to focus molecules from a radioactive source within magnetic shields that reduce the Earth's magnetic field by 100,000 times.
You're trying to produce a millimeter scale single crystal of argon atoms because more molecules could be trapped in it than ACME used to measure the electron-electric dipole moment. Even a 1-second measurement time could match their statistical sensitivity.
Our doped cryocrystals could also be used to search for ultralight dark matter, time-varying fundamental constants, or nuclear antipole moments.
We've demonstrated a force sensor that's 10 times more sensitive than any other solid-state sensor operating at room temperature. The goal is to study the gravitational interaction between a levitating glass bead and a nearby source.
In quantum mechanics, particles can be in a spatial superposition of being in two places at once. How big of an object can we do that with? Is there a fundamental limit? Can we measure the gravity from an object that's in a quantum spatial superposition?
We want to create a quantum spatial superposition and demonstrate matter wave interference with objects 1,000 times more massive than ever before. To achieve this, we need a cryogenic, ultra-high vacuum environment with extreme vibration isolation.
Our Levitated sensor detector is a high-frequency gravitational wave detector that will operate at frequencies higher than most other detectors. We optically levitate small glass particles in the arms of a meter-long interferometer, and a passing gravitational wave produces small changes in the position of the particle. We're searching for signals produced from clouds of axions, a dark matter candidate that would form around spinning black holes.
From observing the motion of galaxies and the bending of starlight, we realize most of the matter in the universe is dark matter, matter that emits no light. It could be particles not included in the standard model. The CFP is working to identify what dark matter is.
We search for ultralight dark matter by using a laser to very sensitively probe changes in the lengths of optical cavities. Within a cryostat at 4 Kelvin, our cavities are hung from pendula to isolate them from vibrations.
At the CFP, we showed that quantum jumps of a novel 1-electron detector could be used to look for 1 millielectron-volt dark photon dark matter 75 times more sensitively than had been previously possible.
Atom interferometers leverage the interference of quantum mechanical atom waves to provide sensitive probes of new physics such as dark matter.
Along with collaborators, we're building a 100-meter tall atom interferometer at Fermilab to search for dark matter, pursue gravitational waves from new sources, and probe quantum mechanics at large scales.
The atom waves must bounce back and forth many times between atom mirrors to amplify the signal of interest. LIGO follows a similar approach, but with light waves, and benefits from highly reflective mirrors that minimize light lost on each bounce. But it's much harder to make highly reflective atom mirrors, which was previously thought to seriously limit the sensitivity of atom interferometers. We optimize our atom mirror sequences so that the collective effect of hundreds of mirror bounces compensates for the imperfections of single mirrors, leading to a factor of 50 improvement in signal amplification over what was otherwise possible.
The Standard Model is the great triumph and the great frustration of modern physics. The great triumph is that it has so far been able to predict what we measure at the CFP and other laboratories to an incredible precision. The great frustration is that the Standard Model is either inconsistent with or unable to account for central features of our universe. The students, postdocs, and professors of the Center for Fundamental Physics at Northwestern University relish the challenge of tenaciously pursuing tabletop precision measurements and sensitive searches to unravel this great mystery of modern physics.